So we are going to look at a problem of a flea jumping off of the ground. And this problem reads, a flea jumps by exerting a purely vertical downward force on the ground of 1.2 times 10 to the negative fifth newtons. A breeze is blowing parallel to the ground and causing a force of 0.500 times 10 to the negative sixth newtons on the flea. The flea has a mass of 6 times 10 to the negative 7th kilograms, and we want to know what is the direction and magnitude of the acceleration. So what we're trying to solve in this problem is what is the acceleration of the flea. Okay, so we're interested in acceleration. We have a bunch of forces. This is a force analysis. So let's start with our object. We are interested in examining the forces acting on the flea. And so what types of forces are acting on the flea? Well, we know that there's always that force of gravity acting on the flea. It's a massive object, and so that's between the flea and the earth. We also know that the flea is in contact with the ground, and so there's the force of the ground, which we often will call a normal force. And so that's between the flea and the ground. And then we know this wind is blowing. So we have the force of the wind, and that's between the flea and the air. So the wind that's blowing on the flea. All right, those are the only forces acting. So let's draw our free body diagram of the flea. All right, so there's our flea. We have the force of gravity, which we know acts purely vertically. So here's our force of gravity. Just as a friendly reminder, that's mass times gravity. We have the force of the wind, and we're told that that air is blowing parallel to the ground. So that force of the wind is horizontal. And since the flea is there on that that horizontal ground, we know that the normal force is acting in the upward direction. So those are our three forces. We label those three forces 1, 2, and 3. And we can look at the horizontal and vertical components to determine the net force's influence over the motion. So let's do that. So we have our horizontal and our vertical. We have three forces. Our first force is purely vertical, nothing horizontal, and it's in the downward direction. So we're going to remember that minus mg. Our second force, purely horizontal, force of the wind, nothing vertical. And our third force is purely vertical, acting in the upward direction, so it's positive. So there's our three forces. There are only components in their respective directions. Now, we're interested in the acceleration overall of the flea, and so we can't make the assumption, in this case it's not even true, that one of the accelerations is at 0. And so we're going to apply Newton's second law, recognizing that there is a horizontal component potentially to the acceleration and a vertical. So the sum of the forces horizontally are going to give the horizontal component of the acceleration. The sum of the forces vertically are going to give the vertical component of the acceleration. So we have the force of the wind is equal to the mass of the flea times the horizontal component of that acceleration. In the vertical direction, we have that normal force minus the weight, mg, is going to equal the mass times the vertical acceleration component for that flea. Well, we're given the force of the wind. We're told that it is 0.5. 0.500 times 10 to the minus 6th is going to equal my mass, 6 times 10 to the minus 7th times the horizontal acceleration. So if I plug that into my calculator, I have 0.5 times 10 to the minus 6th divided by 6 times 10 to the minus 7th. And I get an acceleration equal to 0.833, and that's my horizontal component of the acceleration. What about vertically? I want the vertical component of the acceleration. So I need the normal force that's not in my list. The normal force isn't listed. But what do we want to remember? Well, the normal force is the force the flea acts on the ground. Newton's third law tells us that the force the flea acts on the ground is the same as the force the ground acts on the flea. The normal force is the force of the ground acting on the flea. Newton's third law tells us that has to be the same as the force the flea acts on the ground. So we want to recognize Newton's second law here. The force that the flea acts on the ground is equal to the force the ground acts on the flea in magnitude. And that's our normal force. So we actually have the normal force given to us. It's 1.2, there's a little break here. 1.2 times 10 to the minus 5th minus the mass of 6.00 times 10 to the minus 7th times 9.8 is going to be 6.00 times 10 to the minus 7th times the vertical acceleration. So if we do this out, we have 1.2 times 10 to the minus 5th minus 6 times 10 to the minus 7th, the quantity minus the quantity times 9.8. And then we have to divide that by 6 times 10 to the minus 7th. And we get a vertical component of 10.2 meters per second squared. So now I have my horizontal component, my vertical component. How do I get the acceleration? Well, the magnitude of that acceleration is going to equal the square root of 0.833 squared plus 10.2 squared. And so I get a magnitude of my acceleration. I take the square root of 0.833 quantity squared plus 10.2 squared. And that gives me 10.23 meters per second squared, but I need to know the direction. And so that direction is the inverse tangent of my y component over my horizontal component. And that gives me an angle of 10.2 divided by 0.833. 85.3 degrees. So here is my acceleration. So a magnitude of 10.23 meters per second squared at 85.3 degrees. So not straight up because you got that wind coming into play, but pretty close to straight up. We determine those forces, recognizing the acceleration is in two directions, and solving for that acceleration once we have each component. Now there's another way you can do this problem. We could have first found the resultant vector, the net force, which in essence is kind of what we're doing here. So we could have solved for the net force and then applied Newton's second law purely to the acceleration. We would have still had to have gotten that angle, knowing the angle of the net force is going to be the angle of the acceleration. So that's another way to do the problem. It's really the same number of steps. It just has a little bit of alteration in your conceptual approach. All right, good job.